so just a little bit of background. Let's just review what we just talked about in 7.2. We're talking about the solubility of a compound in water. So here we have iron chloride, which is soluble. So when we first put the iron chloride into water, I mean like the moment we put it into water, there's no ions. Okay, so it's just this. And then like within a millisecond, it starts to dissolve and to break apart. So what is this dissolving into? Well, we have lead chloride here, so it's going to be lead 2 chloride actually. So it's going to be dissolving into lead 2 ions. Okay, and there's only one ion for every mole of lead 2 chloride. There's only 1 mole of lead, and there's going to be 2 moles of chloride ions. Okay, and as this dissolving continues, and as the concentration of the lead 2 increases, and as the concentration of the chloride ion increases, there's going to become a point where in the solution, in the beaker, where they start bumping, these two start bumping into each other. And when they bump into each other, then the solid reforms. So it goes back to lead chloride here. And so we see here, as the lead bumps into the chloride, it's going to get lead chloride. And then this lead chloride is going to dissolve back into lead ions and chloride ions. Well, as these two processes are happening at the same time, ultimately, it's going to reach what's called an equilibrium, a dynamic equilibrium, where the front reaction, this reaction, is going to be happening at the same rate as them going back together. And so we have this unique arrow that we're going to start using here in equilibriums. That's a double-sided arrow. Sometimes you'll see it like this, but many times you'll see it like this, where it's one arrow on top of the other. And I'll show you what that looks like in just a moment. So that when you see this, that means that it's a frontwards and reverse reaction. So it's a reversible reaction. And that's what solubility is. It's a reverse reaction. Oops. Okay, so from this, we're going to talk about now the solubility product constant. And we can also write an equilibrium expression for this according to what's called the law of mass action. And it involves some calculus, but I'm not going to show you that. We don't need to know the calculus. We don't need to know how this is derived. We just need to know what it is. Okay? And so we take here lead chloride, and it's going to be dissociating into lead ions and chloride ions. So what we do is we write the products of this reaction over the reactants. So products over reactants, and we leave out the solids and the liquids because since we're writing concentrations of liquids don't change and the concentration of solids don't change. And if we just left them in, then eventually in the math of this derivation from the calculus, they're going to cancel out anyway. So we don't, when we write the Ksp expression, we don't leave those in. Okay, so it says here where the lead and the chloride ions are expressed as molar concentration. So we're going to write the brackets around these ions to represent these ions as concentration. Okay, and this constant, Ksp, is called the solubility product constant. So solubility S, product K is a constant. So K in chemistry is used universally as a constant. Or we can just call it solubility product for short. All right, so again, liquids and solids are not used as part of the Ksp expression because their concentrations don't change and they're constant and are going to be canceled out. So the definition of Ksp is the product, see here these two are multiplied, of the ion concentrations in the saturated solution raised to the power of the coefficients in the equilibrium. So what does that mean? Well, see here we have lead. There's no coefficient here for lead, so we're just going to put it as the concentration of the lead ion. So it's lead plus 2. But since we do have this coefficient here for chlorine, this 2, this coefficient is going to be expressed as an exponent here. It's raised to the power of that coefficient. So when we write the solubility product constant, then we use the coefficient as the power for that ion. So the Ksp for lead 2 chloride is the concentration of the lead times the concentration of the chloride squared. Okay, now we left out this PbCl2 here because it's a solid. Okay, so normally this would be over something divided by something, but since this is a solid, we leave it out. So all we have here are the products. I'm sorry, products of this reaction. Okay, and we're going to see some when we get to talking about acids and bases and their solubility products. We'll see where we do leave in that over the reactants. The reactants are left in. But right now, just for solubility, most of the time those are out because it's a solid that's being dissolved in a liquid. Okay? All right, so calculating Ksp. The solubility of a substance is related to its solubility product, and we can calculate one from the other. So for this first example, we have calcium sulfate and the molar solubility. Now you're going to see this word molar solubility, and don't let that throw you, because see here, it's expressed with M. That's molarity. So molar solubility, that term that they use, means molarity. So if you see that molar solubility, don't let that throw you. It just means molarity. All right, so CaSO4, the molar solubility or molarity of calcium sulfate is 8.4 times 10 to the negative 3 moles at a certain given temperature. Calculate its Ksp. All right, so we're going to start with an equation. So we have CaSO4, okay, and that's going to give us Ca plus 2, because it's a calcium ion, plus SO4, and SO4 is negative 2, okay? So the Ksp expression for this is going to be the concentration of the calcium times the concentration of the SO4. Okay? And so we don't have any coefficients here because it's a 1-to-1, because these two canceled out. So we don't have any powers here. Okay, so this CaSO4 is a 1-to-1 relationship, okay? So substituting now in, since this is 8.4 times 10 to the negative 3, since it's a 1-to-1, this is also 8.4 times 10 to the negative 3. And this is 8.4 times 10 to the negative 3. So remember from our last section or our first section, we talked about the law of molar ratios. Same thing here. If this is concentration of 8.4 times 10 to the negative 3, since it's a 1-to-1-to-1, this is going to be the same and this is going to be the same. So now let's substitute that in. So we have 8.4 times 10 to the negative 3, and that's for this one, times 8.4 times 10 to the negative 3 for this one. Okay? And so this is going to be equal to the Ksp. So multiplying these out with your calculator. So if we take our calculator and we do 8.4 times 10 to the negative 3 times 8.4 times 10 to the negative 3, we get 7.056 times 10 to the negative 5. Okay? And KSP has no units. So this constant, there's no units on this. So this would be the answer in the calculator. Now, how many sig figs do we need? Right here, 2. So this is going to be 7.1 times 10 to the negative 5th. That's the KSP. So for that particular concentration of that particular ion. So easy peasy. Okay? So now we can calculate the molarity from the KSP. So we're going to use the same example, CaSO4, but the KSP is going to be given to us, and we need to calculate the concentration, the molarity. Well, this is easy, but what we have to do is kind of work backwards with what we're given. So we have to use what's called an ice chart. Okay, so we have here the equation, CaSO4 yields a Ca plus an SO4. Okay, in this ice chart, this means initial concentrations. Okay, the I means initial concentrations. The C means change. And the E is at equilibrium, when equilibrium is reached. So basically, E is just the combination of the initial and the change. Okay, so what we're doing is we're trying to calculate this right here, the initial concentration. So initially, we have 0 and 0, right? So if we look at this, when we put this down into water, what's going to happen to the concentration of the CaSO4? Okay, it's going to go down because it's dissolving, right? So it's going to go down, but we don't know how much. So we're going to say it's going to go down, use a negative sign, by X amount. We don't know how much. If this goes down by X, since it's a 1 to 1 to 1, if this goes down by X, this one is going to go up by X. Okay? And again, since it's 1 to 1, this is also going to go up by X. All right, so what's the change here? So the change is going to be question mark minus X, okay? And then 0 plus X is X, and 0 plus X is X, okay? Now, we're trying to find the concentration from the KSP. So remember here that this is a solid. Okay, so we're going to ignore this. This doesn't matter because it's a solid. Okay, so since this is a solid, the only thing that matters here is the Ca and the SO4. So the KSP expression, remember, is Ca concentration times the SO4 concentration. Okay, so we're given the KSP, so I'm going to go ahead and substitute that in. Okay, and what can we substitute in for Ca? X and X. So this is really X times X. Let me get rid of that arrows here, so it doesn't confuse you. Okay. So it's X times X. Well, what is X times X? X squared. Okay. So X squared is equal to 7.1 times 10 to the negative 5th. So how do we solve for X? We take the square root of both sides. So if we take the square root of X squared is just X, right? And we're going to take the square root of 7.1 times 10 to the negative 5th. Okay? All right, so let's plug that in. So square root of 7.1 times 10 to the negative 5th is going to be 8.4 2, so the 2 is not going to round the 4. So 8.4 times 10 to the negative 3 molarity. Okay, so that's what X is. So this is X, right? And since it's a 1 to 1 to 1, that means that the concentration of this is also 8.4 times 10 to the negative 3. Even though it's not part of the KSP expression, we know because of the ratios 1 to 1 to 1. That's what it has to be. All right, so that's it for the KSP examples and the ice charts that I'm going to show you for now. And in class, we're going to look at when this is not a 1 to 1 to 1. Because we can have a 1 to 2 to 1, or we can have a, let's see, a 1 to 2, or we can have a 2 to 3 ratio. And so what that does is it gives us different values of X here. So we'll look at those more complicated ones during class, but for this example, we're just going to use a 1 to 1 to 1. All right, so let's make sure that you slap that like button right across the face, and make sure you poke that notification bell so that you know when I put up videos in the future.